Let's start. Thank you for joining. I hope you had a nice Friday at Meeting CPP. I'm really happy to be here with you, and we're going to look at code performance on how to measure it, specifically C++ code. So first of all, just a quick introduction why fast code matters. I think you all know it, but you're all here for various reasons. So I made a very short list. I think the main reason we want fast code is energy, right? Our CPU loves to finish the work and then sleep, kind of like us. So like that's great because we don't need to charge our phone every 2 hours. It's also nice because it's like environmental friendly. The second reason is trend. Not all devices become smaller, but we have a lot of, like for example, in light bulbs, you don't have quad core with like 3 GHz CPU in light bulb. We have like some small ARM CPU with like some small cache. And the last reason we want fast code is, we have some real-time constraints. So there is basically, we need latency in certain domains. For example, the gaming industry, and the audio industry, and then finance. And the finance is the reason I do care about latency, because I work at Optiver, we're a trading company. I'm David Gross, and I'm leading a team here who develop automated trading system. I work here for 5 years. I also teach modern C++ here. It's quite nice because we can I'm able to teach C++ the way we use it at my company. And I develop an automated trading system. On today's agenda, we're going to first look at why we want a microbenchmark, in case you're not really sure why you're here. I will give you some more reasons. What exactly we want to measure, look at code performance together. So there will be a lot of demos. If at any point of time you have some small remark question, or if you see me making some mistakes, please let me know because I'm going to code live. If you have some longer questions, I will also try to keep 5 minutes at the end. And also we're going to look at some common pitfalls. So there are some mistakes that I've seen a lot on internet, and I will briefly go through them. So first of all, what is microbenchmarking? I thought it would be important to kind of define that because we're going to talk about it for an hour. It's not the kind of a term that you find in a dictionary. So I had to come up with my own definition. I'm not sure if you will all agree with it, but that's fine. You don't have too much choice now. So this is basically my definition of a microbenchmark. We have roughly 3 lines of C++. We have 4 statements to accumulate, just as an example, and then this benchmark do not optimize. So I'm not going to present Google benchmark because I think there are many talks from previous years. If you don't know Google benchmark, please watch Chandler Caruth's talks. They're great, and most of the time he uses Google benchmark. I still have to say a word about this do not optimize function in case you don't know about it, because I'm going to use it a lot today. It does not turn off optimization, but it tells the compiler to not optimize a where variable. So it does not turn off optimization, and that's very important because all the examples we're going to look today, they are built with O3. By the way, I don't think that there is any interest really to measure performance of code built in debug, so I wouldn't really spend time doing that. And as reference, I also put just like the argument that I'm using today for GCC. I think the only one I should say something about is F-no3 vectorize. This is exclusively for today's presentation. I think it's nice to disable vectorization because if I show you an hour of SSE on AVX code, you might not really like me, especially at the end of the day. So yeah, for ornamental health, we're just going to disable that today. So these are microbenchmark, 2 line of C++, and then 4, maybe 10 assembly instructions. And this is where we are today. So what is this? So this is like the final boss of Sonic 2. Right? So we're here today because what I mean by that is that it's very important to remember that we are going to look at instruction optimization, and this is really the last stage of optimization. So this is really crucial. I'm only going to say it once, but if you get very excited by this talk, it's great. And you go back home and you start optimizing instruction. Please don't forget to do first all the rest of this list, because that's basically where the biggest gain here, right? So you should look at algorithm complexity, memory layout. There are plenty of talks about the different steps, but I'm not going to mention them for the rest of the talk because we are going to focus on instruction today. So typically from last year meeting CPP, I remember a talk from Andrea on memory allocator. There was a talk from Jonathan Müller on data layout. CPPCon this year, Andrei Alexandrescu spent an hour and a half optimizing a small sort. This is instruction optimization, and so he said himself, you shouldn't have high expectation from instruction optimization. You're not going to get a speed of 10 times when you look at instruction. So in Andrei's talk, usually after half an hour, he's at 3%, 4%. This is kind of like, I set the bar very low, so I'm sure that you're not going to get too disappointed today. But this is basically where we are now. So why microbenchmarking? Most of the time because we want to make code faster. But there is another good reason to do it. The main problem of microbenchmark, and if you find in the literature on internet is highly criticized, is because you have two scenarios. The first scenario is you have some numbers and you think they're correct, and they are wrong, and this is actually quite dangerous because everybody look at them. And the second scenario is that you have some numbers and you know they are wrong, and then it's frustrating. So that's basically the problem of microbenchmark, because it's so hard. It's either dangerous or frustrating. I think also that there is it's not very popular because a lot of people on the internet take basically a one-liner, like I did previously, a one-liner of Java, one-liner of C++. Then they just measure that a billion of times and they say, see, this is faster, this is slower. And it's not, it basically doesn't tell you the full story. So I'd say if you wanna have one measurement, in general you wanna have your measurement from production, not from a microbenchmark, right? If it's very fast in the microbenchmark, but then it's slow in production, eventually basically the production measurements matter. The microbenchmark numbers, they're not going to help a lot. Right, so now that I've just discarded the entire reason of my talk, so what are we going to do? So this is my proposition for today. We're going to micro-benchmark to understand, have a better understanding of the code. And what I mean by that is not just the code, but like all the different layers. So like you have the C++ assembly, you go basically to the operating system, kernel, drivers, CPU, memory, the different level of cache, the interaction with hardware, and we will see just by looking at one line of C++, we can learn a lot. And basically, when you go back from Berlin, Monday you will be at work. Just pick a function, like the most boring function, like some function. Just take it and benchmark it. Try to have some expectation in it, and you will see that you will learn a lot. And you will try to optimize. And if at the end it's slower, just revert your changes, and you will have learned a lot about your code, I'm sure. But on the long run, it's going to pay off, basically. On the long run, the understanding that you will have from hardware and from how basically the C++ code translates, this is going to pay off, right? You will be able to design and architect a faster application, right? So this is our goal for today. So what are we going to measure? So usually, as human, we want to start measuring time. I thought I had to start with time. We're going to spend most of the time today not looking at time, but I had to at least say a word, especially because the keynote was on Stud Chrono, so I thought, I have to say something about it. So, but basically, for microbenchmark, it's not ideal. First of all, we don't really need this kind of clock, right? When you microbenchmark, you just need a wall clock. You don't really need the accurate date and time. So basically, the overhead that we have from the various clocks from the STL is not really needed. Now, I also put a slide on high-resolution clock because I think naturally, when we want to measure a time in benchmark, we tend to pick high-resolution clock, and it's not the right choice. If you take anything, take steady clock. And the reason is simple, is that steady clock is guaranteed to be steady, which is extremely important. And for my measurements, it's in general faster. And if you want to use high resolution clock, I think you should definitely at least add those static assets. But yeah, as I said, we don't really need to pay this override. So in general, we're going to use the TSC. Now, I'm not going to say much about the TSC because I would hope, so who is familiar with the TSC or who already uses the TSC? Yeah, see quite a lot of hands, so that's good. So I'm not going to spend too much time on that. So this is basically very low overhead wall clock time provided by your CPU. Now, I think one thing that I don't think so many people know is that initially the TSC was designed by Intel to count CPU cycles. And this means that the TSC, because it was counting CPU cycles, not TSC cycles, and this means that it was great to measure code performance. Unfortunately, what happened is that developers, we started using it, and we just divided by the frequency to measure time. And what happened is that later on there were all the power management features, the P state, C state, so basically dynamic frequency scaling on the CPU sleeping. And and if you divide by the frequency, but the frequency varies by a factor 4, it doesn't work really well. So yeah, what happened is that the developers complained, and surprisingly or unsurprisingly, Intel fixed the TSC. So they basically fixed. Initially, I mean, they were right. They were basically just giving us what was great, basically measuring CPU cycles. And then they fixed it by isolating the CPU to a different power domain. So what happens is that when the CPU frequency change, or when the CPU just idles, when CPU sleeps, go to the kernel and you run halt, like the Intel halt instruction, the CPU basically, you have this, it's called constant TSC, this flag that you have in /proc. The TSC basically just continues. So it means that it's at the same time a very good news and very bad news. It's very good news if you want to measure time, because you can. And it's very bad news if you want to measure code performance, because you want cycles and not time. So I'm also a bit surprised that TSC is so widely used, because it's basically not great to measure code performance. So what you want, and that's basically what we are going to use the rest of this talk, we want basically hardware counters. So there are various ways to access hardware counters. First of all, tools. I just mentioned a few tools here for reference. We are not really going to use them. I think there are also enough talks that use perf, I think mostly from Chandler Carruth as well. So today we are going to look at really tiny benchmark. And for that we will see that perf, although it's an amazing tool that I use all the time, if you measure like really short a fragment of code, there is too much overhead. And you want to use RDPMC directly or PAPI. We're going to use, that's going to be our focus today. We're going to use those two APIs to measure code performance. So the RDPMC, is great. It's basically low latency performance counters in userland. Which means that you can access all your performance counters without going to the kernel. And it's even better than that. You can program RDPMC to tell you, hey, I'm only interested in the events that are in userland. So even if your code basically at some point goes into the kernel, they're not going to be counted. Or you can say nkernel or both. 40 cycles on Intel Skylake versus 25 for the TSC, so it's really cheap. And it's really easy, so like another good news, it's really easy to access those. That's the code. Yeah, not much to say about it. You see it's just basically 4 instructions to access each counter. So all in all maybe 44, 45 cycles. So let's just use them. So I prepared some demo. I hope that everything is going to work as expected, because I always find it's more interesting when you look at things. So this is basically the first very short snippet of code. By the way, is this big enough? Can everyone see the code? Yeah. Good. So what we are doing here, it's quite straightforward. We are reading our counters before and after. In the middle, we are calling 10 times RDTSC. that doesn't really matter, basically just some instruction that you want to measure. You can imagine that you have some code here. And in between, you see CPU ID. So CPU ID is like deserializing instruction in Intel. I think you already heard about it. It basically just avoid instruction reordering on the CPU level. There is always this do not optimize here, which is compiler barrier, right? So if I remove this do not optimize, the compiler, GCC is going to figure out that I'm not doing anything with CPU ID. CPU ID is going to get removed, all these instructions are going to be reordered by the CPU. Right, so let's just run this. And it does not work because I was playing with some stuff. Right. So you see that, okay, I just run that like a few times. You see that there is a bit of jitter. That's not going. You cannot avoid any jitter at all. But you see that the instruction counter is really accurate, right? 31. Yeah, I could show you the assembly. We could count, but it's 31 instructions. That's really accurate. On the cycle, you see that it's kind of accurate. But you see sometimes there is a bit of outliers. But that's basically it. With just 40 cycles, you get instructional cycles in userland. I found that quite amazing. So basically, forget about the TSC and start using RDPMC. I'm really surprised that basically this counter is not used so much because it's quite it's really nice that you can access that for such a cheap for just basically 40 cycles. This is mostly here for reference. You saw me typing some commands when I thought, oh, it's actually not working. So me basically quickly typing some commands. Those two slides are here mostly for reference. Basically, you have to, when you start using RDPMC, and probably that's the reason it's not used that that often, because they are quite complicated. So you have to program that, and you have to look at the Intel software manual. This is your holy book. You have to look at it. I put for reference what you have to do in 3 steps. You have to set some registers. There are many more details, but you just have to look at it. It's in 3B, a system programming guide. But those are basically the 3 commands that if you just basically type them, you can just use the code that I show. But okay, so we just measure instruction, just measure cycles, and you're like, oh, this is great, but why not just, why is this better than measuring time? Well, I think you all heard about IPC, instruction per cycle. So just give me an idea on how much I should do. Who heard or who already measured IPC? Right, quite a few hands. So IPC is basically the reference, right? If you want to measure, if you want to look at one metric, one KPI on your code and evaluate performance, you should look at this. Now, I also include here microbe per cycle because I think maybe it's not more interesting, but you have to know the difference between instruction and microbes. So the hardware, the CPU, basically does not execute instructions. It only executes micro operations. Basically, what happens is that you have your front-end CPU, which decode instruction into microbes, and your backend only deal with microbes. So it's more interesting when you measure performance to look at it from the microbes perspective. So what I mean by that is that typically here we have some addition. So we just do an add from memory to a register. And this is quite a complicated instruction. So this instruction effectively is going to be split into 2 microbes on a CPU. Okay, so why is this interesting? Because when you optimize and when looking at instruction optimization, you need to know when to stop. It's actually quite nice, right? I mean, you can optimize, and at some point, you need something that tells you, okay, this is basically the speed limit. You just reach it, you at full speed. You can remove some more cache misses, branch prediction, etc. You can improve the code. It's actually useless because you reached your full speed limit. And on this architecture, I mean, I showed my laptop, it's Skylake, but on most recent server, it's also Skylake. This limit is 4 microbes per cycle. You're never going to go faster than that. That's why basically it's more interesting than instruction per cycles. yeah, because of what I said, that they don't really map exactly, but they relate. Right, so what's a good IPC and what's the maximum IPC? So the maximum IPC I already told you. You can just open the Intel manual, and it's 4. Now I always like I just like to find stuff by myself. I think it's always good to basically look at it from more like from basically a more practical angle. This is some code that you can just write and run to find the maximum micro or the maximum IPC. It's very basic. By the way, so I just put volatile here. It's just to tell the compiler that my knobs have some important side effects. And then the compiler is just going to believe me, say, oh yeah, important side effect, not going to touch those knobs. If you remove volatile, it's just going to figure out those are just knobs and just remove them. So let's just run that. Yeah, obviously it doesn't do much. So here typically I'm going to use a perf. Let me find this beautiful. Yeah. So here I ran a perf stat, and I basically am interested in three things, 3 counters: cycle, instruction, and microbes. So you see that perf nicely display the instruction per cycle. But if you look, you have the number of microbes here, and you see that we have basically 4 microbes, which translate to 5 instructions per cycle. And the reason we have these so different numbers here, you can just look at the assembly. So that's basically the reason it's interesting to look at the assembly and to know the difference between instruction and microbes. So you see that this is our loop. We have 3 knobs, subtraction on a branch, on a jump. And what's going to happen is that because we have loops everywhere in our code, all the modern CPU are going to do what we call fusion. We're basically going to take the sub on the jump. I'm going to fuse those 2 instructions into 1 micro operation. So this is basically just a kind of trick that the CPU does, because CPU architect knows that we have loops everywhere. So they just fuse those 2 instructions, and we just go from 4 instructions per cycle to 5. That's nice. And this is basically the reason it's interesting to look at microbes per cycle, because with that, basically, you kind of know what to expect by looking also at your assembly. You can you know when exactly you're going to reach full speed. Right, so I wanted to include this picture, mostly also just to mention this website, because it's a brilliant website. It's called wikidchip.org. And I would just advise all of you, like, when you start microbenchmarking, please just go to wikidchip.org and look at your CPU architecture. It's much more comprehensible than the Intel manual. It's quite simple. You have some nice diagrams, and this is basically part of it, not the entire diagram of Skylake. And we can reason about it. So if I just zoom a little bit, just copy the. Let me just zoom. Yeah. So I'm just going to zoom here. And here you see that on Skylake you see 4 LAUs. So you see you have this port 0156. You see it's written LAUs. So that means that we can have basically addition, subtraction, all the instructions you can have on the LAUs. And the knobs that we just executed are going to be on the LAU as well. Right, the knobs is a real instruction that's going to be executed and retired by your CPU. So each knob needs to be on 1 LAU. So we have 3. And then we have the branch. That's our 4th microbe. And you see that on port 6, you see it's written branch. That's basically where all our branch instructions are going to be executed on the CPU. And here we see with this graph, we see that that's basically how we reach like the full speed, right? We're going to have our 3 knobs, 1 on port 0, 1 on port 5, 1 on port 1 on 5. And then we are going to have the branch on port 6. And that's it, basically. We don't have any port available anymore. I mean, you see some port on the right, but those are basically to load and store data. So it's really nice because with such a simple example, you can already reason and see that yes, on every single iteration of the loop, basically the CPU is going to execute one iteration of the loop per cycle, right? 3 knobs in parallel with the branch as well. Right, so that's nice. So it's a nice start. We looked at IPC, but we can do even more, right? We have plenty of hardware counters. On here, my advice would be, so for the IPC, if you want the lowest overhead possible, use RDPMC. It's great. If you want to measure, if you want to use other hardware counters, please use PAPI. I mean, you can use RDPMC, but it's not going to be easy. So if you can afford just a little bit more overhead, please use PAPI. So PAPI is basically provide some abstraction on the top of performance counters, because basically what is hard if you need your code to be slightly portable is like all the more complicated performance counters. So typically L1, L2, L3, data instruction cache, TLB, bunch prediction, and so on. They will all be available with different codes. So quickly, the code is going to be really complicated because depending on if you're on Haswell, Ivy Bridge, Skylake, or whatever, or AMD, you will need basically different codes. On this library, basically takes care of that for you. On here, I just included a command that you can run, and you can basically see, like on this machine, you can kind of like see all the different hardware counters that you can access. And basically, you're just going to specify a string now. On the library, just with this string, is going to map it to, depending on the architecture, is going to map it to the correct code. So it's quite convenient. It's quite nice. So PAPI is a C library. I always prefer to access C++ API, so it's not very fancy, but I just wrote 50 lines of C++ just to access it in a nice C++ fashion. So it's really not fancy. It's really just 100 lines of code. But this is basically how it works. You create an event set. You mention all the hardware counters you would like to use. In this case, cycle and instruction, but you can access other ones. You start your counters, and then you have your code. You stop them, and that's basically how you access them. That's all. And as I said, there is a bit more overhead. I don't remember the exact. To be honest, I mean the numbers are not. It's not entirely simple to get them, but you're not going to have 40 cycles in general. You're going to pay more like 200 cycles or so. So depending on your need, you're just fine basically paying that. I think in microbenchmark in general, it's fine. In production code, though, you might want to just stick to the previous to RDPMC. Nice. So let's just now. So we looked at a few different concepts. Now let's just use that to look at some more code on demo. So we're going to look at a very small example. This is the code we are going to optimize. We're going to measure the performance of this code for the next 10-15 minutes. So the code is relatively simple. What's happening? Sorry, I didn't show you all the code, but that's not very interesting. But we just generate a vector, just random integers. We have 10,000 elements. It's worth noting that on this laptop, the cache, the L1 D cache, is 32 kilobytes. So we have basically 10,000 elements, 40,000 bytes. So it doesn't fit entirely in our L1, so we can kind of expect some cache miss, but not too many, right? And then we generate it. We do this for each, kind of like as a warm up to put things in the cache, and then we call stud min element. Stud min element, returns iterate on the minimum element. We just display it to make sure that it's not optimized away. Any question on this code before we start? Nice. So the first thing we want to know, obviously, is how fast is this code. So I can just start by running it. Cool. So yeah, minimum of some random data, not very interesting. So a second attempt could be to run perf. That's usually what we do. We just run perf start, and then we get immediately the IPC here, right? So that's all. That's nice, but in this case it doesn't work, right? It doesn't work because you see that we are at so what is this? 4 million instruction, 4 million cycles. Yeah, this is definitely much more than our stud min element. I mean, I hope. So the problem with perf is that we are measuring everything. Like we are just measuring everything, the start, the end. We are measuring the allocation, the generation, and that sounds great, right? We only want to measure the IPC on the performance of stud min element. So how do we fix that? Any guess? Say again? Yeah, exactly. Thanks. Good answer. I was actually not expecting that. So usually, that's indeed the good answer, but usually people fix that by not doing that, but by, so there are two ways you could fix it. You could increase the number of elements. This is really wrong, right? I hope that you see that you're fundamentally changing the benchmark by doing that. Because if we change the number of elements, we are changing the working set size, and we are going to just measure something else. Right? The data is going to suddenly be more in L2, and then maybe more in L3, maybe even more in RAM. So it's just going to change entirely the benchmark. Now, what you could do, you could also just add a loop around a min element. I think that's what most people do, and I think this is more reasonable. But now there are other problems with this approach as well. With min elements, so min element is not going to change, it's not going to mutate a vector, but first of all, sometimes you have some mutating algorithm like stud sort. So that's the first problem. But even more problematic, and that's kind of like a hidden effect, is that the CPU is going to learn all your branches. And you will get the amazing performance because the CPU will just predict correctly all your branches, because yeah, you just ran it 1 million times. What would you expect? Sure, like all the branches are correctly predicted. And this is quite annoying, right? You at least if you do it, you have to be very, you have to make sure that you correctly document that. Because it's not going to be exactly your code performance, it's going to be your code performance after 1 million run, which means the CPU, the data is going to be hot, the CPU is going to correctly predict your branch, and everything will be great, stars aligned and everything. So in this case, what we want to do, you said we can use PAPI. Yeah, in this case, I didn't start immediately by using PAPI, but I just wanted to measure the IPC just to kind of give us an idea of like how fast or slow is this code. So I did basically so it's the same code. The only thing is basically the same as what we looked at before. I just use basically RDPMC to measure instruction on cycles, and then I just display that at the end. And I also displayed the number of cycles per iteration. I think it's an interesting measure also of performance. So let's run that. But actually, before we run that, what's your expectation on the IPC? Min elements, stud vector, everything in the L1. Any guess? I want at least one number. It's going to be an awkward silence. Huh? We have 3 here. 3. Everybody's happy with that? 2.5. Good. We have 2 numbers, 2.5, 3. Let's see. None. No. So so this is kind of like classic. So what happened here? That's also nice why we do this live demo stuff is because you remember those 2 slides I quickly skip as this is kind of like a boring, not very interesting, but for reference. Basically, what happens is that every time you use perf, perf is going to be very nice and is going to clean. Right. So perf is basically going to clean all the performance counters when it basically exits at the end basically of the process. So every time you use perf, if you use RDPMC, you have to kind of like enable those again. Right. Now we go. So I think two things, at least two interesting things. First of all, it's it's very slow. On the second one, the numbers are quite stable, right? Like we have like 0.8, 0.85. Like it's quite, that is great, right? Means that we are looking at some nice numbers. There is no jitter. The cycle per iteration is at 7. It's also fairly constant, so that's great. So those numbers looks correct, but they're quite disappointing, right? We're always looking at stud vector. We think stud vector is blazing fast. Minimum element of stud vector should just be fast, right? But no, it's super slow. So, yeah, now we need some IDs, right? I don't know how to make these things faster. IDs. Sorry, I didn't hear. But I did use the STL algorithm, or did I miss? Oh, not to use it. Yeah, but I would like to use the STL. Oh, I mean, okay, we indeed, if I don't use the STL, but but I guess maybe before we were looking for like faster solution, how would we analyze the, like, because now we know it's slow, great, but how do we know why is it slow, basically? How do we basically find the reason it's slow? Yeah. So that's so that's a good answer. I just said one word, assembly, so let's just look at the assembly. So, no, I'm not going to look at it like that. So I'm just going to dump the assembly here, and then we will just find our functions. Our function min element, it's here, we see it. Right, so it's a very small function, right? So we have it here on the entire screen. We see that's basically the start, here that's the red, and here in the middle we have this the body of the loop. So what's going on here? So we take AX, put it in a register. Cool. We compare the register we just loaded from memory to DX. Then we have our CMove. So CMove, that is basically the conditional move for our to basically take the minimum if the element is smaller than the previous one. So now we know here we do the add on DX. So we know that DX RDX is our current element. Now we know. And the other one is the pointer to the current minimum. Right? So RDX current element, RAX current minimum. Yeah. And now we can just, maybe we can do two things, right? We can just think about it, or we can use some like, amazing tool. Maybe I'm just going to put 20. Right, so what did I do? I extracted the loop in a separate file, just like assembly file called min.s, and now I just use LLVM MCA. So who knows LLVM MCA? I see 3 hands. Cool. That means you're going to get really excited because the first time I discovered this tool, I was like, this is amazing. This is really this is just mind blowing. So LLVM MCA is the LLVM machine code analyzer. And what it's going to do, it is going to unroll our loop and it's going to display how the loop is being executed on this CPU, on this architecture, Skylake. So this is amazing, right? Because we could basically just try to basically see how it's being executed, but this tool just give it away. So it's so we see here on the left we have the number on the very left is basically the iteration number, and you have different letters. Sorry. So we see E is basically this instruction is being executed, executing. This is executed, the instruction is being retired. And equal means we are basically just waiting. So equal is bad. That's basically the recap. Equal basically means you're just, the CPU, those cycles are just basically like stall cycles, are just waiting. And what we see here is that between the different iteration of this loop, between like 0, 1, 2, you see that some instruction are being executed in parallel, right? So we have out of order, speculative execution, branch prediction. Those nice features, they work, but kind of, right? They work for the addition and the comparison and the branch. But that's nice, but basically for the C move, the move and the comb, they don't work at all, right? We are basically, so the CPU, our CPU now is executing iteration after iteration, kind of sequentially, like in the old days, our move on C move. So why that? Why is that? Because there is a dependency, right? There is a dependency between every iteration of the loop. The problem is this RIX. The C move has a destination RIX, and on the next iteration, we load from RIX, right? So this is basically a loop carry dependency. And because the dependency between every iteration of the loop, there is no way that the CPU just can't do out of order execution, because it has to wait for the result of the first iteration to do the second to the third, and so on and so forth. And that's basically the reason we are stuck at a bit less than 1 IPC. Yeah? So yeah, how do we how do we make this? So now that we understand kind of like why slow, how do we make this code faster? Second? Yeah. Yeah. So you said several run of minimum. Yeah. So we could do that, but there is something a bit surprising, right? Indeed, minimum is something that you don't really need. You don't really need the dependency from the previous iteration, right? So I mean, you're right. You're on the right track. Yeah. Sorry, can you repeat? Yeah, exactly. So you basically just need to. So in this case, we clearly see that the STL algorithm is used. It returns the iterator on the entire generated assembly is basically using the iterator. Yeah. So you basically propose, can you just keep that in the register, because then you don't have this dependency. Yeah. Indeed. So that's the that's how you make it faster. And what's interesting is that you achieve that with just one character change, right? So actually, it's good news and bad news, right? I mean, it's bad news if you don't know about it, but the good news is that GCC, as soon as you so now I just dereference the iterator. Okay, I'm going to just rename this because that's not great, right? Now the good news is that as soon as I dereference this iterator here, GCC will say, oh, actually you don't use the iterator, you just want the minimum, the minimum value, not the location, right? And if you do that, so let me just show the previous IPC. So we were at 0.8, I think you remember, but yeah, so that's our previous, we were at 0.85, 7 cycle per iteration. That's great, right? I mean, so we just got a speed up of like times roughly between 3 and 4, right? And what happened here is that if we look at the assembly again, to look at it again, right here. So let me just extract that. just put it here. And hang on, did I do that correctly? Did I recompile this thing? Hang on. That's basically the live joy of live demo. What is correct? This. And now, right, just going to look at it again. You think that I should dereference stud mean element? You know what? I'm going to do it because apparently nothing else. So this is the joy of this on this thing. All right, let's look at it again now. At least you know it's live, in case you weren't sure. And I think I know what's going on. Oh, hang on. I know what's going on. So basically, what happened is that we have basically two kind of this function min element stay there, and we just look at the assembly of min elements. And what happens is that GCC inline this function, and I was looking at basically the min element function with the iterator. While in my code, when we basically dereference that, it's basically inline. So that's, yeah. And now I have the correct assembly. Gosh. That's right. So it's because of inlining. We were just basically looking at the unchanged code. No, now we see a big change, right? We see that we don't have the loop carry dependency anymore. Like things are executing in parallel. It's big difference. And by the way, if you just, so here you can specify a number of iterations to LLVM MCA. And this tool is so amazing that if you go on the top, it actually gives you an estimation of the IPC, which is in general quite accurate. So I think you should still measure it, but basically it just gives you a nice estimation of this IPC. Right, I'm going to move on, but this tool, there is so much to say about it. It's very amazing because it gives you also the port pressure per iteration, per instruction. Yeah, we could spend like the entire talk just looking at LLVM MCA. So now, where are we? We are at 3 IPC. We can effectively make this thing a little bit faster. With basically what you proposed, you said, hey, we could basically have multiple min in parallel, so we can basically go a bit further. I already prepared that. It kind of looked like that. So it's basically just now 2 min. We just basically iterate through the two portion of our vector. And the reason it is faster is that this way, yeah, the out of order and speculative execution of the CPUs are just going to cause more cache miss, right? So you're just going to, that's basically the only reason those features are here. They're just basically here to load in advance all the data to basically have more cache hits. And with this, so I'm just going to run this version. You see that yeah, you see that we had 4, roughly, kind of like. So we're still not at the fastest, but that's basically almost it. Because we know that with the loop, we can be up to 5. So let's go back. I still have a few things to tell you about microbenchmarking, because we looked at how to make measurements, but there are also those things that I've seen so many times on the people do it wrong. I got it wrong so many times myself. First, just a note on statistics. Please watch the talk from Brice. For I think like 3 years ago at CBPCon, there is a very nice talk on benchmark. He spent a good part of the talk on statistics. Please watch it, it's great. I just say that, yeah, usually I look at minimum, median, and standard deviation on used boost accumulators. We don't need to reinvent the wheel here. You have to tune your hardware. This laptop is getting extremely warm for that reason. So what did I do here? What is this? This graph is basically just consecutive calls of the TSC. So I just have a vector, and I'm just calling TSC in a loop, and I put that in a vector, and I look at the difference between two consecutive calls of TSC. And I get this beautiful graph. So can anyone guess why do I have 4 or 5 buckets of values? So basically, I'm not sure if you can read on the left, but this is time, so it's in cycles, actually not in nanoseconds, that's a mistake. And we have basically, on the very bottom of the graph, you have kind of a bucket of values that are at 40 cycles. And then you have some of them at 60, 80 cycles, and on the top we go up to 160 cycles. So what is the reason, why did I get those 4 or 5 buckets of values? Any guess? A second? Thermal throttling, yeah, that's exactly the reason. So thermal throttling, in other words, yeah, P states. Right, so at the very beginning we mentioned P states, those are performance states. They are very nice. Mostly, it's basically dynamic frequency scaling. So most of the time, especially on a laptop like that, when you just have some HTML running, it's going to be at 700 megahertz. And when the CPU gets buzzier and buzzier, it goes up to 2.8 gigahertz. A little bit more with turbo boost. On this difference of 700 megahertz and 2.8 gigahertz, you have a factor 4. This is the factor 4 you find on this graph. And in between, that's basically when the CPU so you don't have just 2 P states, you have, I think, 8. And in between, you have basically all those intermediate values. So this is just a word that if you use TSC, and many people use TSC, you have to be careful because if you basically don't fix the P states, and by fix I mean disable them, you're just going to get some garbage like that. So you cannot really do anything with those numbers. So that's basically just a short list of what you have to do. You have to just kind of like disable everything. So you have to disable P states, so that's dynamic frequency scaling. You disable C states. So C states are not a performance state, but they are idling states. You don't want your CPU to idle. You want to also disable turbo boost because that's not a power management feature, but it's basically just a boost of your frequency. But again, it's going to make your measurement not really accurate. You want to disable non-maskable interruptions. You just want to disable that as well. It's also going to cause some noise. You want to disable hyper-threading. This is also a very important one. Hyper-threading, you're going to get twice more logical cores, but the back end of your CPU, there is no magic. You still have, so typically this is a dual core. I have 2 backends, not more. I have 2 L1 and L2 and so forth. And if you have hyper-threading, is going to be, your results are really going to be inaccurate because the operating system is going to schedule some completely random other process on the same physical core. You're going to compete for L1, you're going to compete for L2. In the example we just looked at, we were sure that our delta is in L1. It's our L1, and we don't share it. Well, obviously the exception is if you run code in production and you're interested in how your code behave on hyper-threading, sure. But I think that's really like the only reason. On last not least, CPU isolation. Again, for the same reason you don't want to share your CPU. And once you did all that, you get this beautiful graph. And that basically means that, hey, your system, you just tune your hardware, and it's all good, and you're ready to make some measurements. Now there are some more and more pitfalls. Last one, I'm doing a walk on a container. So I'm basically just iterating through the container 5 times. reading the address, and I just plot the address. So which container is it? Vector. No, it's actually stood list. So heap is a big problem. When you microbenchmark, you start, your heap is in clean state, and this is already stood list. I still have 5 minutes, so I can run this thing. This is the result, and you see it stood list when you zoom just here. But this. So this is you shouldn't see that if you use a stood vector. This is what tells you it's list. I could also show you the code, but you can basically just believe me on this one. And if I use a different allocator, right? So this is just to scare you, but this is basically just to say that you have to be very careful on the heap. Right, so you can take the most basic micro benchmark. You think, hey, I'm going to measure the difference between stood vector and stood list. I'm just going to go through it to just do the work, and the results are not going to be the same as in production. Right? So if you play with it and you do some allocation, deallocation between your allocation and stood list, you will see that you're not going to get this nice basically linear pattern. You will get the real stood list, the terrible stood list that no one wants. You should anyway not use it, and you will have the real number from list. So heap is a big thing, but for every single thing in benchmark, you have to make explicit choice. So like you have to choose if you want your data to be cold, your data to be warm, in the L1, not in the L1. If you want to train the branch predictor of the CPU or not, you want to choose the state of your heap. And you should also be careful of compiler flags, obviously. So you need to go through all that. And only when all that is done, then you really know what you're measuring. Yeah, so that's basically back to my first proposition. We went through, well, not this code, that's to accumulate, but we went through this code. We looked at a few things, and we see that we can understand a few things better. We went through like some CPU features, and I kept for the very end of this talk a last optimization. Right? I told you that hey, we were here at a 4, like the IPC of 4. We had 1.3 cycle per iteration, and to be honest, I tried to optimize this code. And sometimes the very last thing that you can do, if you run out of ideas to optimize and to make code faster, you can maybe just. I hope it works. Otherwise, it's going to be. You can just ask the compiler, right? It's subtle. But we went from 1.3 to 1.0, and effectively, if you look at the assembly, we basically optimized 2 moves. We are at 4.2, right? So I can just remove it. Yeah. So yeah, that's basically the end of my talk. If you run out of ideas, you can just ask your compiler, and yeah, if you ask in a polite way, maybe it's going to be faster. All right, thank you very much. I think we have 2 minutes for questions. No questions? Yeah, if you wanna also drop by, I will be at the Optable booth just on the right. Yeah, thank you very much. Thanks.